Hey there, in this video we're talking about polymorphism in C++ object-oriented programming, and this covers sections 15.6 to 15.8 in the Gaddis textbook. So polymorphism. One of the biggest, most important, most powerful concepts in object-oriented programming. So I'm so glad you're watching this video. Now to begin with, this works very closely with the concept of inheritance. So I'm kind of assuming that you've watched the prior video for that. And in that inheritance video, we built this ongoing example where we have a graded activity parent class for any kind of college assignment that has a grade to it. And then that had a pass-fail activity child class where the grade's only P or F for passing, failing. And then actually that had some child classes from that as well. Obviously the graded activity has a score, and it's got a get score and a set score function that all the children have, stuff like that. And we're also kind of assuming that you just know what the word polymorphism means in standard English. And if that's new to you, that's a term that comes from biology, polymorphism, and it means a creature or an object that has multiple forms, has more than one form or structure. So as one example, a butterfly would be a polymorphic creature. Starts off as a caterpillar, totally different shape, and then at some point it undergoes a transition and it becomes a butterfly with a totally different body form. There's a lot of creatures in the world like that that are polymorphic. Now, for me, as someone that worked in video games for a while, what comes to mind is if you know the fantasy game Dungeons and Dragons, D&D has a magic spell called Polymorph, and you cast it on someone and it changes their form magically. So that's the spell that can turn someone into a character, into a frog or a pig or a dragon or something like that. So that's the polymorph spell, changing something's form. Now, in object-oriented programming, what that's going to do is you're going to allow class objects to take actions like they're another class, basically. Specifically, C++ can track objects in a class hierarchy and call appropriately redefined functions automatically. So you'll have a reference to one type of object, and it's going to wind up acting like another type of object. That's polymorphism there. It's going to give us a lot of power and a lot of flexibility and a lot of efficiency there. So a big idea. I hope you're going to be amazed at what you're about to see in this video. And sometimes the first time people are introduced to polymorphism, they're stunned. They kind of like are just stunned by it. So it's something you're probably going to want to study and think about and reflect and meditate on for probably a long time. But this is a major part of object-oriented programming, and our systems kind of rely on this quite a bit, so you definitely want to know about it. Okay, let's start here. Pointers to the base class. Again, for this to work, you have to have a class hierarchy with parent and child classes all kind of connected, like in the last video. So here's one thing you can do. You can define a pointer to a base class object, and you can assign to it the address of a derived class object. So here's an example of that happening here. We're making a graded activity pointer. Remember, graded activity is the grandchild in our ongoing class hierarchy example. We're making a graded activity pointer called exam. And then over here, we're dynamically allocating, for what it's worth, dynamically allocating a new pass-fail exam object, calling the right constructor. Gets allocated on the heap as usual. You're going to get the address of that new pass-fail exam object. Take that address, store it in this pointer called exam, which is of type graded activity pointer. Now, if you think about it, that right there ought to blow your mind. Because if you think back to chapter 9, we always said that's impossible. We specifically said you can't intermix different types of pointers. We said an integer pointer is a different kind of thing from a float pointer, is different from a string pointer, et cetera, and you cannot assign one to the other. If you go into the IDE and you try to take a float pointer and assign it to an integer pointer, the compiler prohibits that. It's disallowed, compiler error, right? Any other type of pointers you try to mix and match and it's not allowed. You cannot take a string pointer and assign it to a character pointer. Totally different types of things, completely disallowed. But here we are completely breaking that rule somehow. Okay, so this actually is allowed, and this actually will compile, and it's the one way that you can break that rule. Let's think about why that is. The conceptual reason why that makes sense and here's where that grammatical concept from the last video comes in, is that a pass-fail exam, which is in that class hierarchy under a graded activity, a pass-fail exam is a graded activity. It's a special type of graded activity. So it totally makes sense to refer to this as a graded activity. And that's why this is built into C++, and that's why this makes sense to work, is because a pass-fail exam, well, it is a graded activity. It's one special type of graded activity. All the stuff about a graded activity this has, it has all the same member data, it has all the same member functions, plus some more stuff, but it makes sense. It totally is a graded activity, and that's why you can use a graded activity pointer to store to the address of one of these things, because it is one of those things. Yeah, and so once you do that, you can start doing this. You can call exam, right, that's this graded activity pointer, arrow get score. You can call exam, pointer to the get letter grade function. Now remember, those are both two public functions that were originally defined in the graded activity class. Again, if you go back and look at that example. So get score was defined in graded activity, get letter grade was defined there originally. Every single object in the entire class hierarchy has these public functions. So it makes sense to call it on that pointer. And of course, every graded activity has those functions, and this totally works. Now, there's a lot of details we should think about exactly how does that work after all, but it makes sense, I think. Okay, so here's what you can do with that. So granted that a graded activity pointer can potentially hold the address of anything in the entire class hierarchy, here's an important function from program 1513 in the book. This is called display grade. And as you can see here, the display grade function displays a graded activity object's numeric score and letter grade, just like we're talking about. This version of the function uses a graded activity pointer as its parameter. Okay, so the function is called display grade. It does some printing. It's got a void return type, don't worry about that. And it takes in, for its one argument, it takes in a graded activity pointer. Calling it activity, right? Setting it const, because this function is not going to change it at all, a graded activity pointer. And there's some numbers coming out, so they set the precision on the numbers, and it prints out the activity's numeric score is activity arrow get score. And remember what that's doing is it's dereferencing the pointer and then going to the particular member function of get score. And it's also printing out the activity's letter grade is activity arrow get letter grade. Okay, so it prints out the numeric score and also the letter grade. Now, the interesting thing is that because that parameter to this function here is a graded activity pointer, you can pass in a pointer to any of the objects in the entire class hierarchy. You can pass in a pointer to a graded activity object, obviously. You can pass in a pointer to a final exam object. You can pass in a pointer to a pass-fail activity object. You can pass in a pointer to a pass-fail exam object. You can pass in a pointer to a curved grade activity object. Why? Because they're all graded activities. Yeah, they're all just special types of graded activities. So they count as graded activities, and therefore you can pass all of those things in this function, and that is accepted by the graded activity pointer, because they all count as that type of thing, plus more special stuff. Okay, so here we have one single function to do printing for all that stuff, and now I don't have to write a separate piece of code to print out a graded activity versus a pass-fail activity versus a final exam, right? I just have one single function that handles all of those different types of objects. That just saved me a ton of work. That just saved me a ton of work from having to write 5 different functions for this. I just write one. And this one function accepts any one of those types of things. Okay? Again, it has to be in a class hierarchy for this to work, but then you can just make a function that takes a pointer to the grandparent type object, and you can pass in any type of thing that you want. Fantastic. Love it. Now, this here, we're doing pointer syntax on the argument. You can also pass in a reference. So this could have been graded activity ampersand type activity, right? Works the exact same way. Again, really reference variables are just pointers in disguise, so it's totally the same thing. Same idea there. Now, the question is, so this works and it compiles and it does something, but the question is, like, if I pass in, for example, a pass-fail activity, that was our example from the last video about redefining functions. Graded activity has its version of getLetterGrade that returns A, B, C, D, or F, whereas pass-fail activity, the child class, has a redefined version of getLetterGrade that only ever passes back a P or F. So the question right now is, if you pass in a pass-fail activity pointer to this function, which version of getLetterGrade gets called? Is it the base class version that prints out A, B, C, D, or F? Or is it the child class version that passes back P or F? That's important. So we're going to talk about that on the next couple of slides. Which one would occur? Okay, now to begin with, if you're working with a base class pointer, a parent class pointer like we're talking about there, the base class pointers and references only know about members of the base class. So if I have something that's defined as a graded activity pointer, right, I can arrow to the getScore function. I can arrow to getLetterGrade because those things were defined in the original base class. It has to be stuff that the base class knows about from that pointer. So stuff that got added in later classes, like the setMinPassingScore function that was in pass-fail exam, you cannot access that from a base class pointer because the base class pointer doesn't know about that kind of thing. You can try it. It's going to be a compiler error. It's going to say, I don't know what it means for a graded activity pointer to have this extra thing. That wasn't defined in this type of class. So yeah, you can't use a base class pointer to call a derived class function. Okay, but it's different, right? GetLetterGrade is not in this category because GetLetterGrade was actually originally defined in the graded activity class. So here's the answer to the question I posed in the last slide. Redefined functions, like getLetterGrade, things that were redefined in the derived class, will be ignored. Only the base class version will be called. So on the last slide there, if I have a graded activity pointer, like exam arrow getLetterGrade, then it's going to call the graded activity version of that function, right? The graded activity version of the function, getLetterGrade, will get called and return A, B, C, D, or F, only from the base class. Unless we use polymorphism. If you don't like that, here's how we're going to switch it up. If you don't like that and you want to call the redefined version in your child class auto-magically, this is what polymorphism is. So here we're about to change things up in a major way. Here's the other option. So if you want your pointers, your base class pointers, to honor the redefined functions in your child classes, you have to make those functions virtual. So a virtual member function is a function in a base class, in the parent class, that expects to be redefined in a derived class and will automatically transform itself to do that. So how you do that is you tag your function prototype with the word virtual. So here I have virtual, return type, name of function, in my parent class, right? The very first thing in that prototype there is going to be virtual, saying this here is a function that's going to transform itself into different forms depending on the child class. And what that's going to do is you're telling the C++ compiler to use dynamic binding on the function call. What that is you're going to do some extra work in the compiler at runtime to keep track of this pointer. It's really aiming at which type of object, right? I got this graded activity pointer, but I have to do some extra work in a table behind the scenes to keep track of. Now that one's really a pass-fail activity, and this one's really a final exam. And this pointer here actually is a graded activity, and it's going to virtually keep track of what kind of thing the object really is. Now you see that's different from what happens without the virtual tag. Without virtual member functions, C++ uses what's called static binding, whereby when you compile the program, it just locks down the pointer function calls to whatever's in the base class. And of course, that's really more efficient. It's faster, so why not? Just lock it down. I got a pointer to a graded activity, the function's in the graded activity class, of course. But if you want to use polymorphism, you tag it with virtual, and then it says, okay, I don't even know what it's going to be. I'm going to have to keep this dynamic table while the program's running, and it's going to change. This pointer is going to be one object now, it's going to be one object, a different object later on. So you don't want to mark every single function as virtual. You only want to mark the things that you know are going to have to be redefined and be accessed in functions from pointers like this. So we don't make everything virtual, just the stuff we know has to be redefined, because it does have to do extra work to keep track of this while the program's running. Okay, so let's take a look at that. So here is that graded activity example from the last video. There's nothing different about this at all. Nothing different except for one thing. Okay, it's got the same score member, it's got same constructors, same mutator, same accessor, same getLetterGrade function. The only thing that's changed here is we tagged it with virtual. Right, just this one single word on line 27 is different from how we saw it last time. So just tag that with virtual. And now, if you access child objects via a base class pointer, via a graded activity type pointer, now, instead of calling this version of getLetterGrade, now you're going to call the child's redefined version instead, polymorphically. So you're going to have one pointer calling getLetterGrade, and it's going to call different versions of that function from the same line of code, polymorphically. Let's kind of look at this program 1513 here, right? And remember, we have those two different versions of getLetterGrade that we've seen before. So program 1513. So we have this function, we saw it before, this function called displayGrade that takes a graded activity pointer and therefore is happy to receive a pointer to anything in the class hierarchy. Pass, fail exam, pass, fail activity, final exam, right? Any of those things, it's happy to receive any one of those things. We've seen that before. So here we are testing it. On line 12, we're making a graded activity object called test1, right? It's got an 88 score on that. And now we're creating a pass-fail object, right? New type of object, pass-fail exam object, calling this test2. And if you look at the details of that example, a pass-fail exam has got a number of questions being stored, the number of questions that were missed, the minimum passing score to determine whether you get a P or F grade after all. So it's actually recording the individual questions in that type of object. And now we're going to pass both of those things into the displayGrade function. So here we are in line 21 calling displayGrade and passing in the address of test1, which is actually a graded activity. And then on line 23, we're calling displayGrade and we're passing in the address of test2, which is really a pass-fail exam. Okay, it totally compiles, this totally works. Passing in pointers to different types of objects as long as they're in the same class hierarchy. And of course, a pass-fail exam really is a type of graded activity, so it makes sense. And now we're back to this function that we've seen before. So we just got to get to reflect on this again. displayGrade. In comes a graded activity pointer, which actually could be any one of those things. And you're going to print out the numeric score with getScore. And you're going to, at the last line here, you're going to call the getLetterGrade function, and you're going to print out the activities getLetterGrade. Great. Now we return to that question that I had before. So now the question is, again, when the pass-fail exam pointer in that main function there gets passed into this function, which version of the getLetterGrade function will now be called? Will it be the one from the base class that only prints out A, B, C, D, or F? Or will it be the one that got redefined in the child class, the pass-fail activity, that returns a P or F? Which one will happen now, based on our changes on the last couple slides? Okay, so if you're following what we're saying here, of course, you know what the right answer is. Let's take a look at this code here in the IDE. So I am currently looking at the lecture code in chapter 15. There's a folder called Graded Activity version 3 is what I'm looking at. And you can see there's quite a bit of code happening now. So I've got the header and implementation file for these three classes in the graded activity example. Several different test drivers in here. What I'm looking at is program 1513 is what I'm doing. So for that multi-file project, I've made a project here and I've had to put in all of the different source code files for all three different classes plus the test driver 1513. So quite a large number of files are now being included in a project. And this is what you can just kind of imagine if this expands to even larger programs, what professional programs look like. So the reason I need all this stuff, here's the actual test driver here, is that program 1513, right, it makes a graded activity object, and it also makes a pass-fail exam. Well, in order to do that, it's going to include pass-fail-exam.h. Let me jump over there, pass-fail-exam.h. Now, pass-fail-exam itself inherits from pass-fail activity, and it also adds the individual question tracking that's here. Not too worried about that. But that inherits from pass-fail activity, so this had to include pass-fail-activity.h, okay, which is over here. And of course, we've seen this before. Pass-fail activity inherits from graded activity. This is where you get the min-passing score and the version of getLetterGrade that prints out P or F. So this had to include GradedActivity.h. Okay, so that's why I needed this. And of course, here's the original parent class, GradedActivity, that originally set up the score and the get score accessor. And again, here's the original definition of the getLetterGrade function. And again, it is marked virtual here. So I'll just kind of briefly look through the source code because we've seen this. Here's the GradedActivity's original version of the getLetterGrade function that returns A, B, C, D, or F. Here's the version of that child class. Here's the version of getLetterGrade that returns P or F. And then what we're also seeing here is pass-fail-exam, which inherits this. So pass-fail-exam inherits this from pass-fail-activity. And then pass-fail-exam also has this set function that takes the number of questions, the number missed, and sets up the percentage grade for the score. Not too worried about that, but it does the job. Okay, so back in PR 1513 here. And again, the question is, you make these two tests of two different types. You pass both of them into display grade. Okay, you drop down here. And in particular, for the second one, that's really a pass-fail exam, pass in that address, it's accepted as a graded activity pointer. When you get all the way down here to the last thing that's going to happen, which version of getLetterGrade will be called? The one from the parent class that returns A, B, C, D, or F, or the one that got redefined, the child class that returns either P or F? Let's see. So I'll compile all this stuff. See, now the compile's taking a little bit longer. And I'm getting all these object files. Every one of the CPP files has its own object file. Linker came through, glued it together in this executable file. And now I'm going to run it and see what gets printed. Okay, so for the first test that actually was a graded activity, you get the numeric score of 88, and the activity's letter grade is B. Great. And then for this child class, this one right here, pass-fail-exam test 2, you pass that into the exact same function, and it says the activity's numeric score is 75%, right, because they missed 25 questions out of 100, and the activity's letter grade is P. So you can see here that we're getting the P or F result, that it is calling the child class's redefined version of getLetterGrade. And of course, that is actually what we wanted. And so interesting. So this one line of code on line 39, right, activity arrow getLetterGrade, is potentially calling two different functions. One time it called the base class version of getLetterGrade, and another time it called the redefined version of getLetterGrade from pass-fail activity, actually. So one line of code that's actually calling two different functions polymorphically, taking a different form, right, tracking it with the dynamic binding and potentially taking a different form depending on what type of object actually got called in. Kind of interesting, powerful thing. So let me make one modification of this, right? If I go all the way back to GradedActivity.h, where that function was originally defined here on line 27, what happens if I take out the virtual? And now obviously I'm back to how we saw this originally back in the original video for chapter 15. So now I'm going to hit, I need to be careful about this, I'm going to hit rebuild all, because change this header file, and then it changes the derived header files, and it changes all the code that's dependent on it. So I have to rebuild everything here to be careful about it. Okay, so there's that. And now if I go back to my program and I run this now, see now for the pass-fail activity, the pass-fail exam, it actually does print out a C because now it's calling the original parent class version of that function. So no virtual, now you're stuck with static binding, and the only thing you can do from a graded activity pointer right there is to call the original parent class version of that function. No virtual, static binding, just calling the parent class version of that function. And now you see a C, which isn't really appropriate for a pass-fail exam. That's not really what I want here in this particular case. So go back here, fix that up, put back the virtual, and now you've got the dynamic binding again. Now you've got polymorphism actually happening again. And I can come back here and run this, and now you're back and actually seeing the P, because again, now I'm calling the child class redefined version of that function, which is what you really want. Awesome. So you can see here that the normal thing in C++ is for your functions to be statically bound. So all of this stuff is statically bound, and you only go back to the parent class function if you call it from one of the child classes. If you want dynamic binding for C++ to track what type of object it really is, you have to do this special thing and tag it with virtual. Now, as a little side point, see, other languages might take a different tactic about that. For example, Java went the other way around. In Java, all your functions are actually dynamically bound by default. That's the normal thing. And if you don't want that, then in Java, you have to tag your functions with the word final to say that I don't want dynamic binding, I want static binding instead. And as usual, the differences between C++ and Java, C++ is saying, I assume that I want everything to be as fast as possible. So probably static binding, because that's the fastest thing. You're locked down with the one function call, and there's no extra lookup table, super fast. Whereas Java is saying, I assume that you want things to be as efficient and easy for the programmer as possible. So I'm going to make it dynamically bound all the time, and I don't care about my programs maybe being a little bit slower as a result. And that's the constant debate between C++ and other languages, like Java, is C++ made the special thing virtual, and Java did the opposite, and you have to tag it with final if you don't want that. So a little interesting distinction that I keep in mind sometimes. Okay, so that's a big idea, right? That's a big idea about polymorphic objects. You have a base class pointer and a class hierarchy. You have a function that can handle any one of those things. Pass in your pointer there, and as long as the functions are marked virtual, then you call whichever redefined version in the children have automatically by dynamic binding, right? And C++ is doing a lot of work behind the scenes to keep track of exactly which type of object it really is. And then one line of code, one single line of code is actually polymorphically calling a bunch of different functions, which is interesting. So that already is a huge idea, right? But here's an even bigger idea. So we're not going to stop there. Here's an even bigger idea at the end of chapter 15. C++ has the idea of an abstract base class. And it's not the only language like this, right? If you have object-oriented programming, you're going to have this idea. An abstract base class is a class, get this, that serves as the basis at the top of a class hierarchy, but cannot have any objects instantiated on its own. So you make a class like this, okay, it's going to be the parent of some other classes, but you cannot make any objects of this type of class. And obviously, all my students always ask, well, why would you want to do this? You're making a class that you can't make objects for? Why on earth would you want to do this? And we definitely need to answer that question. So this does provide, we do this a lot, and this does provide a good starting format for any child classes. So whatever the common traits are, like the, being able to get a score or get the letter grade in the graded activity example, whatever the common traits are, why not set that up in this base class, inherit it into all your many child classes for free, instead of repeatedly rewriting that in the child classes. You can just put it once in the base class, and then you just get it for free in all the child classes, the ones that you actually are going to make objects for, even if it doesn't make sense in the base class to have objects. All this stuff is going to get inherited all through the class hierarchy and save yourself time that way. And you're giving yourself a convenient target type for polymorphic function calls. So again, I can write one function to receive pointers to anything in the class hierarchy, and even if that parent pointer can't actually really be an object, it will receive all the child class objects and work perfectly fine. So you're setting yourself up to be able to make these generalized functions to handle anything in the class hierarchy, even if the parent at the top never actually has any of its own objects. Okay, so this actually is very useful. How do you make this happen? So a class becomes an abstract base class when at least one of its member functions is made pure virtual, which we'll show you on the next slide. Now, just a little side point here, C++, we call this abstract base classes. Other languages might call this different. For example, Java calls this idea an interface. So if you want to do the same job in Java, they have a totally different keyword for it. It's not a class at all anymore. Now it's an interface. But this is something we definitely want to do, and Java has a separate keyword just for this. Okay, so C++ though, abstract base class, you want to do this, you make a function pure virtual. And here's what that looks like. So a pure virtual function, something inside an abstract base class, is a function that has no implementation code, right? You're going to have a prototype in your base class, and the base class at least has no code to it at all whatsoever. Therefore, in order to work, it must be overridden, redefined in a derived object class, which is actually going to give it some code. So if that's what you want a pure virtual function, you tag it with equals 0 at the end of the prototype. And that's how you communicate to the compiler that this actually is a pure virtual function. I know I'm not giving it any code, right? Be on the lookout for some child classes where the code's actually going to be. So a good example here, again, it's a virtual function. It only works with virtual functions. Virtual, void, or whatever return type, y, or I'm sure better function names than that, whatever your parameters, and then equals 0 at the end. And now you've got a pure virtual function in your master base class. Now, details here, again, you cannot have any code in the base class when you do this. This is the whole point. The base class doesn't have code for this function. Therefore, you can't make an object of that class because it's not complete, because you don't have code for some of the functions. So you can't make an object because you couldn't call some of the functions if you did hypothetically. As soon as you make even one function like this, I mean, you can make 1 or 2 or 3 or 4, but as soon as you make one, the class becomes an abstract base class. Cannot make objects of that base class. If you want to make any objects, you must have a child class that then overrides that function and actually supplies real code. Then you can make an object of that child class, and all the functions have code, right? And that's how that works. Okay, so again, why would you want to do this? Let me give you an example of at least one important situation where you've got a parent class that you cannot instantiate. All right, so let's take a look at, the C++ standard library uses this concept quite a bit, uses inheritance and a class hierarchy and polymorphism and abstract base classes that you can't instantiate is actually built into the input-output functions that you've been using all along in C++, and you didn't even know it. But this is how the C++ standard library is set up. So let me start looking at the bottom here. Okay, so we know what an IF stream is, right? That's an input file stream from the fstream library that we looked at in chapter 12, right? And we know what an OF stream class is. That's an output file stream for output files, either text or binary, again, that we looked at in chapter 12. Okay, where does that stuff come from? Well, little new thing that you're learning today. An IF stream is actually a child class of a parent class called iStream, which more generally, not just for files, stands for input stream. Any kind of source of data with bytes coming from someplace into your program. Could be a file, could be a network, could be the keyboard, right? Those are all iStream's input streams. So you have this more generalized parent class called iStream. For example, sin is an object of type iStream, right? Sin just happens to be a globally accessible object that's defined of type iStream. That's exactly what sin is, okay? And then over here, OFStream is a child class of a parent class called OStream, which more generally represents any kind of output stream, anywhere where bytes are flowing out of your program. Could be a file, could be the network, could be the monitor, could be a printer. Okay, anything that you're sending information to counts as an O stream. For example, count is an O stream, right? Somewhere in somebody's header file there, there's an object of type O stream that happens to be called count. And that's exactly what count is. It's a type, it's a type O stream is what it is. A special type just to send stuff to the console. Okay, now where does that stuff come from? Now that both branches there, and you know, there's other stuff I didn't even put on the slide here. I mean, there's F streams we didn't talk about, things like that. There's a generalized IO stream class, but let's not worry about that. So further up the class hierarchy, both of these branches are actually inheriting from a class called iOS, which is just a generalized class for the input-output system. It has some, you know, generalized rules for how input-output's going to work. There's bytes, for example. There's bytes, and they move around. And that's what the iOS class defines. And then there's actually a parent up above that called iOS base for the input-output system's base class. Okay, so here's a good example of a class hierarchy that I'm just taking a couple important slices out of. Now, as you can see here, iOS base is a base class that cannot be instantiated. You cannot make an object of type iOS base. If you do it, the compiler is going to deny you. Cannot do that. Okay, so it seems like that would be totally useless. But every single one of these things counts as an iOS base object. So SYN, count, IF streams, OF streams, they're all special types of iOS base, of the iOS base class. So as a result, one thing that I could do is I could make a function that accepts a pointer to an iOS base. Okay, now you can't actually make an iOS base object, but if I make a function that takes a pointer or a reference to an iOS base thing, then I can pass any of these things into that function. I can pass SYN or count or an IF stream or an OF stream or literally anything that I want in this class hierarchy. And then that one single function can do a job that I need to do. For example, like it says down here, get or set the field width, like the thing you're dealing with the set width function from IOmanip, or do set precision, set the decimal precision on that object, right? Or there's other formatting flags you can deal with because they're all inherited from iOS base. So every single type of object in this entire class hierarchy knows about field widths and decimal precision that's been set to and other formatting flags. So instead of writing a bunch of separate functions to handle SYN and count and IF streams and OF streams, I can just have one single function that handles all of them. And that's the advantage to having a base class at the top of the class hierarchy, even if I can't instantiate things of iOS base. I've set myself up for a very efficient single function that handles all of these things. So hopefully that makes sense why, like one case where it would make sense and be useful to have a base class that you can't actually instantiate, but you've set yourself up for very efficient processing with all the stuff that descended from it. Again, in Java, it's called an interface, setting up the interface to classes that are yet to come. And this also explains why insertion and extraction are so similar between SYN and IF streams and count and OF streams, because they're literally the same thing. They're all I streams, right, for the input stuff, and they're all O streams for the output stuff. So sometimes if there's some kind of printing task that I want to do, I make a function that takes a pointer of type O stream, and then I can pass in count, or I can pass in an OF stream pointer, and I can do that same kind of printing, whichever type of object it is. They're both type O stream. So very, very convenient and sets yourself up to be very efficient with your programming. Now you're building with big pieces. And that explains why that was so easy in chapter 12. And it also explains why all the IOmanip stuff works identically in all these objects, because they're all iOS base classes. Fantastic. Love it. Okay, so that's the power of polymorphism right there, right? Really setting yourself up to be very efficient programming later on. So there's some big ideas. This is probably the biggest ideas that I know about in object-oriented programming. So I would recommend that my students read book chapter 15 and really kind of reflect on these really big ideas here and how this helps us out. Practice with the review questions at the end of chapter 15. Going to have my third test coming up pretty soon. So look at the learning management system for the practice test 3, what you're going to be looking at. We do have a programming challenge I usually assign for chapter 14. And then at this point, if you want more practice on object-oriented programming, my top recommendations would be challenges 13.1, 13.11, and 14.8. And chapters 13 and 14, actually, I feel is the important things for what I'm going to be asking people to program on test number 3. And of course, my students would get together to practice this in a lab here. And what we would do is get graded activity version 3, where we've built out this whole class hierarchy here, in chapter 15, test program 1514. And what they have there, I believe, is they have an array of graded activity pointers, but they're actually set to dynamically allocated different types of objects. There's like one graded activity, there's a pass-fail activity, one of them is a final exam object, one of them is a pass-fail exam object, I think, like in an array, actually. And you have a loop, and you just pass every single one of those things into the display grade function that we've been looking at a couple times, I think. And so I'd be asking my students to read the specification changes, what's changed in our class hierarchy since the last time we saw it, test this program, and see if you can predict what do you think is going to be printed. What do you think is going to be printed if I start passing a whole bunch of different object pointers into the display grade function, which of course accepts a whole bunch of graded activity pointer type things. And you know, one of the functions, the display grade, is marked as virtual in the parent class. And so the other question I would ask is, what would happen, what would change about the program if virtual was removed from the parent class specification? And of course, if you watch this video carefully, you know what the answer is. So if you're one of my students, I'll see you for that soon. When we come back next, the next video, we're going to get into the last part of the course. And of course, we're going to get into chapter 16 on templates, which are even another continuing advancement on our technology that sometimes relies on polymorphism, as a matter of fact. So I hope you'll join me then, and I'll see you for that.